What the heck? Ta-da! Let's get something straight, Papa. I want to contribute to your Christmas, to your Advent calendar. And so I challenge you. I challenge you to a challenge. I want you to do this problem. Given an isosceles Christmas tree, where these side lengths are x and that one's 1, imagine you have stacked inside of that equilateral Christmas trees in such a fashion that the largest Christmas tree shares a base with the big Christmas tree. And you have these infinitely stacked equilateral Christmas trees forever to the limit in the tip. In terms of x, what is the total area of the equilateral Christmas trees? Fröhliche Weihnachten.
Papa Flammy's Advent Calendar.
Here. Good morning, Invitations. Welcome back to another video. Thank you, Sam, for the very spicy chipmunk introduction, but doesn't matter. He presented the problem to you and I'm going to show you my way of solving it today. I gotta be honest here, I pulled a fresh toad walker off because I wasn't able to solve it completely. I was not able to turn my final formula that I derived using analytic geometry into an explicit formula that was with respect to the slant length d. I called it d instead of x here. So I wasn't able to do that. I got a bit of help from him, but it does make perfect sense after all, after trying around it a little bit. So this is just something I want to tell you guys. Sometimes I fail too, and this was one of the occasions. Other than that, don't forget to check out STEM merch. We got 10% of all the fundamental theorem of engineering merch today, and also 10 to 15% of everything over on my personal Teespring shop by using the code 42069. But before we actually get into the main video, I would like to thank our recurring sponsor Wondershare for sponsoring yet another video here on this channel, and I'm a bit excited because on 27th of November they actually released PDF Element 8. So this is the 8th version of PDF Element Pro, and it's amazing. It's so much faster and it looks very nice. So I'm going to present it to you a tiny little bit and then we are going to dive into the main meat of the video. So for me personally, the upgrade to PDF Element Pro was a huge deal because PDF Element Pro in itself was already the perfect tool for me because I was able to edit each and every PDF how I wanted, the text in there, extract pictures, squiggle around the pages, etc. But it was always a bit slow on its feet. But now with PDF Element Pro 8, it actually looks way better. So the UI looks really great. They got a really slick style going on. But the most important thing is that it's way faster. It loads up faster, it loads the PDFs faster, it scrolls smoothly, it's just overall very perfect now. I just love using PDF Element Pro 8 at the moment and I do not want to go back, honestly. And like mentioned before, it does do everything that the other PDF Element Pro versions already did, but way better. So you can edit PDFs, you can extract pictures, you can permutate the pages, you can delete pages, you can use OCR and everything you could do before, but now way faster and better and way more stylish. So if this feels like it's something for you, make sure to check out the link at the top of the description. With my personal link, you are going to get 50% off PDF Element Pro number 8, and you can try it out for free already down there. So try it out and support the channel this way. It's really worth it. I'm using it each and every day, not using Adobe Acrobat Reader anymore or the likes. PDF Element exclusively. It's a really good program and I love the Wondershare products, to be honest, just like I love Brilliant, for example. Now we are going to dive into the main video. So I tackled this problem using analytic geometry. I have nearly no elementary geometry knowledge whatsoever. This is also what I told Sam when we were talking about the problem, and because of that I had a few problems with deriving the very final formula after I got very far into the problem. So at first let me present to you what basically my train of thought was. So what you want to find out is the total area of all the equilateral triangles that we have here, infinitely many, you can stack them up in total. And for this we are going to add up each and every area, meaning we are going to have an infinite series of areas which hopefully converge. Okay, we are going to talk about the convergence pretty soon. Now for that I created a little function because to find out what the area of an equilateral triangle is, all we really need to know is what the side length right here needs to be. For example, this side length, this one right here is 1, if you didn't know so already. And also we need to find out what the height in this triangle is because if we have, for example, this height right here, I'm going to call it h0 for reasons that will become apparent in a minute. Then this length right here is nothing but 1/2. And well, this side length right here, since we have an equilateral triangle, is also going to be 1. Meaning our side length h0, as a matter of fact, is going to be the square root of, and then we are going to have 1 squared minus 1/2 squared. Meaning this right here is 1 minus 1/4. This is 3/4 in here. Taking the square root of that is going to result in h0 being nothing but the square root of 3/2 after taking the square root. Now, from this height, we can actually get to the area of a single equilateral triangle. This is pretty easy actually, because I have shown this trick before. We have already split it up, and now this part right here, this triangle, is the exact same one that we are having right here. So why not take this triangle, turn it around and glue it onto here, and this way we are going to get a square out. Not a square, it can also be a rectangle. But calculating the area of a rectangle is really simple. We just need to multiply this side length by this side length. This side length in our case is nothing but 1. So the area not, okay, this is the area of the zero of triangle basically, is going to be 1/2 times and our height not basically. Okay, this is pretty easy actually. Meaning overall this right here is going to result, okay, the first one is square root of 3/4 and so on. And the same procedure applies to all the other triangles that we are having. Meaning if we say this right here was the base B0, okay, this right here is the zeroth base of a triangle, then this right here is B1, the first base, B2 is the second base, B3, etc. And we have here, this is height 1, height 2, height 3 and so on. This is how we are going to split everything up. And from this point onwards we can use analytic geometry and just point finding out to actually find out a recursive formulation for all the bases that we are having here with respect to the very first space B1. And this is how far I've got with the area interpretation, the infinite sum. And then I got stuck because I didn't know how to represent B1 using the slant length B. But we are going to go for this route at first, and then we are just going to represent everything at the end. And then we are going to land at a very nice looking, really extremely fucking ugly formula for the area. Let us dive right in. After this long explanation, let us draw a little coordinate system into here. And this coordinate system is actually pretty easy to place. We're going to place it right here, okay? And now we are going to get ourselves a linear function which passes through the origin. Which one is it going to be? Well, obviously this slant length right here is going to be a linear function, let's call it f. And now we just need to find one point in this coordinate system to actually determine what the function f is going to be, because it doesn't have a y-intercept. It does have one, but it's 0, meaning we just need a single point to find out what the slope is going to be. Meaning f of x is a proportional function of the form m times x. So which point can we choose to determine it? Well, it's actually pretty easy. We can, for example, use this point. By using this point, we are going to represent all the other bases and heights using B1. You can choose any other point, for example B2. This way your representation is going to change a bit, but it really doesn't matter in the grand scheme of things. Meaning, what is this point right here? We are going to call this point capital P. And we are going to find out what it is exactly. I mean, finding the y-coordinate is actually really easy. The y-coordinate of this thing is just the height of the first triangle, h0, being square root of 3/2. Okay, that was fairly easy, but what about the x-coordinate that we're having here? We're going to play around a tiny little bit. I'm going to sketch it out a bit more, just half of the triangle. It's going to look like this. Now, this length right here, okay, just imagine cutting everything off and just taking a look at this part. We have our coordinate system running along here. And now, what is this length down here? This length is nothing but 1/2. Now, this length up here is by definition, okay, this is just half of B1. So this right here is B1/2. Meaning, we need to find out what the distance from the y-axis to this point P actually is. I mean, this distance right here is nothing but 1/2 minus b1 over 2. Factoring out the 1/2 is going to result in 1/2, 1 minus b1. Okay, now we got our point P, and determining the slope is now really easy because this is just the quotient of y divided by x of this point because it's a proportional function, really easy to determine. We covered this on the second channel, Flammy 2. Check it out, whole playlist on linear functions over there, it's pretty good. Now, if we were to divide this thing by this thing, the 1/2 is going to cancel out, leaving us with square root of 3 over 1 minus b1 times x. This right here is our function f of x, and it's going to be a very nice tool to determine what all the other lengths, b2, b3, etc. actually need to be. And for this, we are going to put some more points into here. Namely, this right here was, let's say, p1. This was p. Meaning we had some x1 coordinate associated with it. If we go a bit upwards, exactly here, we're going to have an x2 coordinate associated with it. Okay, next up, this right here is x3, is the x coordinate corresponding to the position of our b3 basically, and so on. And now we are going to put a bit more stuff into this coordinate system, namely taking a look at all the heights that we are having in here, and then we are going to determine our x-coordinates, x1, x2, x3, by using our y-coordinates. And the y-coordinates of each and every point right here are just going to be, well, the heights of those triangles. That makes sense, okay? If you take a look at here, this was h0, then the height of x2 or the y-coordinate, where x2 is actually in the coordinate system, is going to be h0 plus h1 and so on up until infinity, up until we reach the highest point. Meaning, let us make this a bit more clear. If we were to scale this up, then the place where our x1 is going to be is exactly our h0 being the height. This is the y-coordinate corresponding to it. Meaning our y-coordinate corresponding to x1, y1, is going to be nothing but, okay, h0 is square root of 3 over 2. Now we are going to go up here. Now we have our y2. This right here is the second y-coordinate corresponding to the second x-coordinate. Where is it exactly? Well, it's at h0 plus, okay, if we put this into here, this is going to be h1, okay? So it's square root of 3 over 2 plus, okay, what is h1 exactly? It goes by the same means that we have derived h0 before. Meaning we are going to take a look at this triangle right here. This right here is our h1. And what do we have exactly here as being our length? Well, this right here is going to be nothing but b1 over 2, obviously, because it's half of b1. And what is this length right here? It's an equilateral triangle, so this is right here is going to be b1. Meaning our height 1, h1, is going to be nothing but the square root of, okay, we are going to get a nice formula for each and every height here. It's going to be pretty good. We are going to get that this right here is b1 squared minus, and then we are going to get b1 squared over 4. Okay, just using Pythagoras. b1 squared is a common factor. Factoring it out, taking the square root, is going to leave us with b1 times the square root of, and then we have 1 minus 1/4. Hey, this is good. This is just square root of 3 over 2 yet again. Ah, this is cool. So meaning, for each and every height that we are having in here, height 1, for example, it's going to be just the base 1, multiplied by square root of 3 over 2. Same spiel with height 2. Height 2 is going to be b2 times square root of 3 over 2, and so on. Meaning we are just going to stack everything up. So here we are going to have square root of 3 over 2 plus square root of 3 over 2 times b1, and so on. We are going to repeat this process up until infinity, basically. But we are just going to find a recursive formula for all the bases, b2, b3, etc., with respect to b1, and then we are basically done with all the heights, with the total height in this triangle being just the height from down here to up here, okay, to the highest point of our Christmas tree. Now we are going to plug our x1 into here and see what we are actually going to get. Then we are going to plug x2 into here and see what we are going to get, and so on. Now, if we were to take a look at f of x1, what is going to be? F of x1 is going to correspond to a certain y-coordinate, and the y-coordinate is just y1, meaning this is square root of 3 over 2. And this is exactly, well, we can't do much here. We can plug x1 into here, but that's basically it. So we are going to get square root of 3 over 1 minus b1 times x1. Cool thing is square root of 3 is going to cancel out, leaving us with x1 being hence nothing but multiplying this by 1 minus b1 under the condition that it's not equal to 0. But we don't want b1 to be equal to 1, otherwise we don't have a Christmas tree anymore. Okay, obviously we're going to get 1 minus b1 divided by 2. Okay, this right here is the first one. Let us go for the second one. F of x2 is going to be. Now this is going to correspond to a certain y coordinate, namely y2 in our case, leaving us with square root of 3 over 2 plus square root of 3 over 2 times b1, being hence nothing but, well, just x2 plugged into here basically. So square root of 3 over 1 minus b1 times x2. Now you might notice square root of 3 is a common factor again. We have 1/2 that we can factor out, meaning this right here is equivalent to saying we have 1 plus b1 over 2 being equal to x2 over 1 minus b1. If we were to multiply both sides by 1 minus b1 under the condition that's not equal to 0, no it's not, we're going to get 1 plus b1 times 1 minus b1, that's the difference of two squares, leaving us overall with a formula for x2 being hence nothing but, I'm going to put this in the numerator, 1 minus b1 squared over 2. Now you might think that we are stuck, but this is not the case at all. If we take a look at our x-coordinate of a point, this right here was point 1, then this x-coordinate actually applies to all the b's that we are having here. Meaning, if we were to take a look at x2, the same argumentation actually holds yet again. So if we were to have this one here, for example, then if this right here is our x2, then we are also going to have that our x2 is nothing but 1/2 times 1 minus b2. I mean, it does make sense. We are going to take the whole base, 1/2 or half of the whole base, and then we are going to just subtract b2 over 2 from it, and this is going to be the difference from the y-axis to our point x2, y2. Meaning overall, x2 is also nothing but 1/2 times 1 minus b2. And this is good. So 1/2 is a common factor. We can cancel it out on both sides. Then we are going to be left with 1 minus b1 squared is hence nothing but 1 minus b2. We can cancel out the 1s on both sides. We can add this to both sides and this to both sides, or just multiply both sides by -1, leaving us overall with, okay, b2 is nothing but b1 squared. This is interesting, right? This is the first step of the recursion that we are having here. And now we are going to go a step further and say, okay, what about f of x3? So f of x3 is nothing but, so on the one hand we are going to have square root of 3 divided by 1 minus b1 times x3 being nothing but, okay, we are going to have this height plus this height plus this height, height 2, being the total y-coordinate in the coordinate system. Meaning, by the height theorem basically that we have derived before, we are going to get that the square root of 3 over 2 plus square root of 3 over 2 times b1 plus square root of 3 over 2 times b2. But the thing is, b2 is nothing but b1 squared. So let's substitute this in. This is really good. I love this part. Square root of 3 is going to cancel out. What we are having here is nothing but, okay, factoring out the 1/2 is 1/2 times 1 plus b1 squared. Okay, and if we were to multiply both sides by 1 minus b1, we are going to be left with x3 being nothing but, okay, this is going to be a nice one, 1/2 times 1 plus b1 squared times 1 minus b1. If we were to factor everything out, so what is this going to result in? We are going to get 1 plus b1 squared, and then just, all of those multiplied by b1, but with a negative sign. So negative b1 squared, and negative b1 to the third power. This is cool. This, and this is going to cancel out, leaving us overall with 1/2 times, this is 1 minus b1 to the third power. And don't forget what x3 actually is. By this point thing that we have here, this point situation, we also know that this is nothing but 1/2 times, this is 1 minus and b3. And And once again, we can cancel out the factor of 1/2. We can subtract 1 on both sides. We can multiply both sides by -1, leaving us overall with, and now here comes the best part, b1 to the third power being nothing but b3. This is really curious. Isn't that cool? I mean, we have b1 to the third power being equal to b3. We have b2 being equal to b1 squared, okay, to the second power. And we have b1 being nothing but b1 to the first power. Also, for the 0th base, we have that b0 is nothing but 1, which is the same as b1 to the 0th power. So meaning overall, you can probably prove this using induction or some shit, I don't care. We have the situation that for Bn, okay, our Bn, this is just the base of the nth triangle, this is going to result in nothing but the first base to the nth power for all n element of natural numbers with 0. Isn't that a cool result? And with this result, we can actually just add all the heights up that we have, okay, substitute b1 into all the other b's, and with the height formula also comes the area formula. And then I'm at the formula that I derived before, and the last thing we need to do is to actually represent our b1 with respect to the slant length. Now we are pretty close to being done. Let us gather what we have found out up until now. And I just love this analytic geometry approach because it's just way more elegant than any other elementary geometry proof out there. It's just really good. So we have found out that we have a height of a particular equilateral triangle in here being just denoted by hn. For example, for the third one, it's going to be square root of 3/2 times base number 3, where each and every base n is nothing but, well, b1 to the nth power. Also, we can represent each and every area, we have discussed this before, as just the height times our base divided by 2. Now we can start plugging stuff into here. Namely, we know what Bn is. This is nothing but b1 to the nth power. This is cool, right? But we now can plug this and this result into our area formula, leaving us with the area of the nth equilateral triangle being hence nothing but, okay, hn is going to be square root of 3/2 times blah blah blah. So this is square root of 3 divided by 4. And now we are going to get b1 to the nth power times bn, but bn is nothing but b1 to the nth power, meaning we are going to get b1 to the 2nth power overall. Isn't that cute? That's a nice result if you ask me. And now we can go ahead and just add all the areas up. This is what we wanted to do. We wanted to add up the area of the 0th triangle, the first, second, and so on up until the infinitive triangle that we're having there. Meaning we are going to take a look at an infinite series, namely a0 plus a1 plus a2 plus dot dot dot, leaving us with an infinite series where n is between 0 and infinity of all of our ans. Well, this is cool, right? I mean, we have an explicit formula for the nth triangle, so for the area of the nth triangle, so why not plug it into here? Square root of 3/4 is nothing but a constant, so we can bring it to the front. Also, we now have this infinite series, n being greater or equal to 0, of b1 to the 2nth power. Okay, now we can go a step further and think back to exponentiation rules, namely if we have b1 to the 2nth power, this is b1 squared to the nth power. So meaning we can drag the nth power to the outside, and hey, we have something to the nth power summed from 0 to infinity. That's screaming for geometric series. Only argument we need here is that our b1 squared is in the radius of convergence, and it obviously is. I mean, if b1 were equal to 1, so the base of our Christmas tree, then we wouldn't have a Christmas tree anymore, because our lines or linear functions wouldn't meet at any point anymore. So meaning it must be strictly less than 1 for it to form a triangle, okay, Christmas tree. And if it's 0 or something, that really doesn't matter, then we have a Christmas tree shaped like an equilateral triangle. So meaning overall, since this b1 is in the radius of convergence, we are going to get that the total area, a total, is hence nothing but, okay, this is square root of 3/4 times, and by the geometric series, this is 1 divided by 1 minus b1 squared. And this is how far I've gotten. And then I didn't know how to proceed further. But then Sam gave me a little hint, which I didn't know existed, namely we can scale up triangles by a factor, and it's going to result into something very nice. I mean similar triangles. Let me elaborate on this. Okay, it has to do with Papa Pythagoras. This is the formal justification that I came up with. We are going to take a look at our Christmas tree yet again, looking like this. This right here is base 1 and first equilateral triangle, and this right here is our B1. Okay, it's going to get interesting from this point. Now let us take a look at one half of this thing. We are going to take this part right here, and this length is the total height of all Christmas trees stacked up. Okay, this is just h0 plus h1 plus h2, etc. So this right here is h total. Now what we also have is half the length of 1, so the side length is 1/2, and this length is, this is our slant length d. Now, by using Papa Pythagoras, since this right here is a right triangle, we are going to notice that d squared is thus nothing but the total height squared plus 1/2 squared. Okay, and now we are going to scale this triangle down a bit. We are going to take this height and we are just going to make it smaller and put it exactly here, okay? Meaning, remember what this height then is. This height that we are having here is just the height from the base of the isosceles triangle to the first x-coordinate, kind of. Okay, if we were to put it here, then it would be the same argument. Meaning, this height that we are having here is nothing but h0. Meaning, we are going to scale everything up a bit. Let's say by a factor of t. We are going to say that this part right here is nothing but td, so it's our slant length, multiplied by a factor which is less than 1, okay, since we want to make it smaller, let's call it d. And then we're also going to have side length down here. We don't know yet what it is. I'm going to justify it in a second, but this height is also h0. Meaning overall, if we have a factor of td, then this right here is going to give us td squared, okay, using Papa Pythagoras, ending up with td squared. This is the same as multiplying this original equation by the scaling factor t. And this is something that I didn't know before. This is the justification that I came up with. We're going to multiply everything by t squared here. And then we are going to get ourselves a scaled slant length, basically. Meaning, by using this right here, we are going to get t times the total height squared, which is nothing but h0 squared. Okay, and this whole thing plus, okay, dragging the t into here, this is going to give us t over 2 squared. Meaning this side length that we're having down here is just 1/2, but scaled by the factor t. I didn't know that something like this existed. I never knew about this. This was new to me, but a surprising fact and a welcome one, to be honest. Now we know what h0 is. This is square root of 3 over 2. And now we are just going to solve for our t right here. Meaning, if we were to subtract this part on both sides, we are going to get, square root of 3 over 2 is hence nothing but, and now we are just going to solve for our h0 that we're having here. This is going to be the square root of, then we are going to have t squared, d squared, minus t squared over 4. Okay, hope you can see where all of this came from. Subtracting this, taking the square root, and then we are at this point. Now t squared is a common factor, meaning we can factor it out, leaving us with t times the square root of d squared minus 1/4. D squared minus 1/4. I would love to factor out the 1/4 here a bit, leaving us with 4d squared, and the square root of 1/4 is going to give us 1/2, leaving us with square root of 3 over 2, being hence nothing but t over 2 times the square root of 4d squared, 4d, minus 1. Okay, now you might notice that 2 and 2 is going to cancel out, or 1/2, the multiplicative inverse of 1/2 on both sides, and by dividing both sides by square root of 4d squared over minus 1, it's not equal to 0, because this can only happen if, I don't know, this can't happen, okay? It just can't happen. Then our d squared must be, or our d must be equal to 1/2, and this doesn't happen by definition of this problem. Okay, then we wouldn't even be able to put one equilateral triangle into here. This just wouldn't happen. Okay, never mind. We have that t is hence nothing but, and then taking the square roots together, is square root of 3 divided by 4d squared minus 1. Whew, there was a lot of talking. Now we know what t is, but how does that help with B1 that we're having here? Well, it gets a tiny little bit better than that, because remember, what is our T? Our T is basically this gap being filled in here on both sides equally, such that we get a length of 1, meaning the length of 1 that we are having here is nothing but, okay, we are going to take the base B1 and we are going to add to it 2 times, and this length is exactly T over 2. Meaning 1 minus 2 and 1/2 is going to cancel out. 1 minus T is nothing but B1. Okay, cool stuff. So we know what B1 is in terms of the scaling factor, but the scaling factor is with respect to our slant length. And this is where the real magic happens, namely we're going to plug everything into here. We're going to get that the total area with respect to the slant length, at the very least, is going to be square root of 3 over 4. 1 divided by 1 minus, okay, and then we're going to have 1 minus T squared. 1 minus T squared is going to give us, okay, square root of 3 over 4, 1 divided by 1 minus, okay, binomial theorem is 1 plus 2t minus t squared. 1 and negative 1 is going to cancel out. We have a common factor of t right here, leaving us overall with a total of d is hence nothing but square root of 3 over 4 times 1 over t times 1 divided by 2 minus t. This right here already settles it for me, at least because we know what t is, but we can also plug it into here. So t is nothing but what we have here, and don't forget we have the square root of 3 up here. If we were to plug it in, square root of 3 and square root of 3 is going to cancel out because we're going to take the reciprocal, leaving us with square root of 4 t squared minus 1 divided by 4 times 1 divided by 2 minus the square root of 3 divided by 4d squared minus 1. And this right here is, as promised, the very ugly looking formula for the total area of all equilateral triangles stacked together. Ooh, that was, haven't done such a huge geometry problem in a while, but was a lot of fun. Can you come up with a solution? Try it out. I thank you guys for watching. If you did enjoy this video, please like, subscribe, make a comment, channel like. Don't forget to check out our today's sponsor, PDF Element Pro, Wondershare, who are kind enough to sponsor this video. Their app is totally worth it. I mean it when I say it. I'm using it every day. So yeah, check it out and support channel this way. Up until the next video, I wish you guys a fun day. Hope you are enjoying the Advent calendar thus far. Ciao.